In this session, we will discuss the summarized experiment data container. This is a more modern or new version of the expression set. We will use an example data package to illustrate it. The example data package is called Airway, and we need to load the data into R, and we can print it. In many ways, this looks superficially somewhat similar to an expression set. It has a dimension, 65,000 rows and 8 columns. So in this case, it means 8 samples and 65,000 genes or exons or whatever it is we have on the other dimension. There's a lot of things that are very similar to expression set, but has a slightly different syntax and output. So what we are used to knowing as P data from the expression set, we access using col data in the summarized experiment. And it returns not a data frame, but a capital data frame, the new type of data frame that was introduced in Bioconductor. As before, we can see that there's some sample identifiers and some information about specific details of the experiment. We can get a column like for expression set by using the dollar operator. So I can say airway $cell and get back that specific column for the thing. As for expression set, this is highly useful. We can look at experiment data, details about how the experiment was made. And in this case, it's pretty empty. We can try to see is there anything in here. There's some information here. We can see which paper which paper where the data comes from. We can see a PubMed ID and so on and so forth. We no longer have sample names. We only have column names, which are really the names for the different samples. And again, we don't have feature names. We have row names. We can see that the feature names look like ensemble gene identifiers. So how do we actually get the expression data? In this case, that's not obvious, but this is RNA-seq data. How do we get the expression measurements? Well, in summarized experiment, we use the assay accessor. In order to use the assay accessor, we need to know what type of assay it is. So first we can look at the printout of the object itself. And you can see in the printout that there's one assay and it's called counts. You can also guess the list of all the assays by writing assay names, which gives us back just counts. So how do we get it? We say assay airway, and we give it the name of the assay we are trying to extract. So this is count. So this is going to be a big matrix. I'm going to subset it so we just get the first 4 genes and the first 4 samples. And here it is. This is RNA-seq count data. The new thing in summarized experiment that you didn't have an expression set was that each row or each feature has an associated G-range or G-ranges list with it. So we access that using row ranges. And let me first get the length of this, row ranges. It's the 64,000 different features we have. We have one range for each thing. So in this case here, the row ranges is not a simple G ranges, it's a G ranges list. The idea being here that each row is a gene, and we get a G ranges list, and each G range in the G ranges list gives us the exons of the gene. So here we can see that the very first gene, the gene that is being measured in the first row, has 17 exons and is located on chromosome X. And here we have the coordinates for the exons. This is very useful because often in next generation sequencing we are measuring things over genomic intervals, and here we can keep the genomic intervals together with the experimental data. So, for example, we can look at how many exons do we have per gene, or how many exons do we have in total. We use element lengths to give us the length for each G range, and we can sum them up. Oh, that was not row data, I meant row ranges. Okay, we have a little typing mistake. So we can see that we have 64,000 genes and we have almost 750,000 exons. Now, there are some of the standard G-ranges functions that you can just access directly onto the Airways data set. For example, if you want to get the start coordinates of all the exons, we can do it like this. This gives us a list with the start date of each exon and each element of the list. In a similar way, we can use subset by overlaps, which is quite useful. So let's say we have a G range that gives us some an interval on chromosome 1, and it shouldn't be chromosome 1 because it uses a different name. So ranges start equal 1 and equal to 10 to the 7. Okay, so this is the standard G ranges, and now I can say, let me just get the genes inside Airways, in Airway that overlaps this specific genomic interval. And it's subset by overlaps. So there's 329 genes inside this 10 megabase genomic interval, and here we have the data for it. So this summarizes the summarized experiment data class. So we access things using row and col. We have the G ranges we can access, and we have the assay function for getting the expression measures or whatever is measured in this summarized experiment.